Greetings everyone. So now we are going to discuss about the types of isomers, which is number one is structural isomer. Isomers are divided into two major types, which includes the structural isomers, as we have previously discussed. What are isomers? These are compounds having same molecular formula but different structure formula. Structural isomers, and second one is geometric isomers. We also call geometric isomers as cis-trans isomers. Cis-trans isomers, right? When it comes to the structural isomers, these are those isomers which are formed due to a change in the position or due to the change in the arrangement of the carbon atoms, or the change in the arrangement of carbon atoms, or the arrangement of functional groups in the molecular formula, due to which it causes to form structural isomers. Structural isomers has got five major types, which number one includes chain isomers. Chain isomers are those isomers which are having um, same structure, which are having same molecular formula, but they have the difference in the arrangement of their carbon atoms. For example, if you talk about pentane, pentane has three major isomers, which number one includes CH, which includes N-pentane, which is straight chain pentane, and pentane. Straight chain pentane and pentane, right? Second one, this is N-pentane. On the other side, we are having isopentane, isopentane, right? Isopentane. Oops, it's CH2. This is CH3. This is isopentane. Isopentane. On the other side, if you talk about another type of pentane, that is neopentane. Isopentane is branched, N-pentane is straight chained, and neopentane is having a structure in which all of the carbon atoms are arranged in a tetrahedral shape, such that in neopentane structure, this is the structure which is found in neopentane. CH3, CH3, and CH3. So this is the structure in neopentane. All of these are basically pentanes which are having different structural formulas and are thus known as the chain isomers. Alright. After chain isomers, what we are having is position isomers. Position isomers are those in which there is a difference in the position of functional group. Let's say if the functional group is present in uh, is present on the first carbon, then it is known as 1-chloropentane. One chloropentane has two isomers on the basis of position isomers, which number one includes 1-chloropentane, second is 2-chloropentane. In 1-chloropentane, the functional group is present on first carbon, and in 2-chloropentane, the chlorine is present on the second carbon as the functional group, due to which the chlorine being the functional group is present on first carbon in 1-chloropentane, and chlorine being the functional group is present on the second carbon on chloropentane, 2-chloropentane. After which third type includes functional group isomers, in which functional group isomers is a one in which the compounds have same molecular formula, but their structural formula varies due to a different functional group which they have. Let's say if we talk about a good example of this includes glucose. This is the general formula for monosaccharides. This is a general formula for sugar. There's C6H12O6. Now this sugar can be uh, aldose sugar. This sugar can be this sugar can be glucose, and this sugar can be fructose as well, because on the basis of the functional group which they possess. Glucose is having functional group as aldehyde functional group, and fructose is having functional group as ketonic functional group, due to which both sugars are having same molecular formula but difference is there in their functional group. Likewise, we have ether. If we have dimethyl ether, we can create a compound which is having dimethyl ether as which is having the same molecular formula as dimethyl ether, but it is different in structure, right? So in that sense, functional isomerism, functional isomers are there. On the other side, we have fourth type, which is metamerism. Metamerism is the one in which there is a single functional group. There is a same functional group of both isomers, but the arrangement of carbon atoms on either side of the functional group is different. Let's say if we talk about dimethyl ether. Dimethyl ether is having a methyl group on either side of the a methyl group on either side of the ether functional group, but when it comes to the methyl and propane ether, methyl and propane ether, methyl and propane ether, methyl, let me just write that down, methyl and propane ether, methyl and propane ether, methyl and propane ether is basically the metameric isomer, the metamer of dimethyl diethyl ether. It is the metameric isomer of diethyl ether. So in the two metamers are belonging to a single homologous series. As we are having a single homologous series in case of diethyl ether, methyl and propane ether, both of these belong to a single homologous series, which is ether group. On the other side, fifth one and last one is tautomerism. Tautomerism or tautomerization is a process in which the organic compound is having a naughty hydrogen. There's a naughty hydrogen atom which is known as the mobile hydrogen atom. That mobile hydrogen atom present in the tautomeric forms causes to um, causes to exist, causes to jump from one functional group to another functional group, due to which it causes to change its position continuously from from one part of the organic compound to another part of the organic compound, due to which the organic compound coexists in two different states in equilibrium with each other. Organic compounds exist in two forms. Organic compounds exist in two forms, due to which the organic compound exists in two forms, due to which the organic compounds exist, due to which the organic compounds, due to which the organic compounds, due to which the organic compound exists in two different forms in equilibrium with each other. In equilibrium with each other. Organic compound exists in two isomeric forms in equilibrium with each other, which is basically what we call as the tautomerization or tautomeric forms, and that phenomena of isomerism in which the two isomeric forms exist in equilibrium with each other are known as the tautomerism. That occurs due to the change in position of from hydrogen or proton from one part of the carbon organic compound to other part of the organic compound, or in other words due to shifting of hydrogen, which is basically known as mobile hydrogen. So this is how we do. This is how organic compound exists in equilibrium form in tautomerism. Tautomerism, right? Let's get an example of that as well. If we talk about amino acid has this formula. This is carbon. This is the radical alkyl group. This is NH2. This is hydrogen over here, and over there we are having COOH. Now, what actually happens in amine group is that the amine group sometimes exists in equilibrium with its tautomeric form, which is known as zwitterine. Zwitterine. Such a manner that the hydrogen which is present in the carboxylic acid group of amino acid is a mobile hydrogen, becomes a mobile hydrogen, and that mobile hydrogen causes to move causes to leave the carboxylic acid group and moves towards the amine group, due to which it causes to produce a structure where the amine group is having an extra hydrogen and it becomes positive, and the carboxyl group as a result of lack of positive charge becomes negatively charged COO minus, due to which this is how a Zwitter ion is formed, and these two forms are known as tautomeric forms. This is not a tautomerization, tautomeric forms are there. All right. And apart from that, if you talk about geometric isomerism, it occurs in double and triple bond compounds, a triple bond and double bond hydrocarbons, such that it occurs in unsaturated hydrocarbon, double, triple bond hydrocarbons, because whenever there is a single bond of an organic compound, when two carbon atoms form a single bond, then they are able to exhibit rotational motion, due to which the position of the atoms on those organic compounds does not really matter. Let's say if hydrogen is present on the upper side, it can be present on the lower side as well, in case uh, there is in case there is exhibition of rotational motion within those carbon atoms, which is only possible in a single bonded carbon atom. But if you are having double or triple bond, then the strength of bond is stronger, due to which the carbon atoms are unable to exhibit rotational motion, due to which the position of due to which the position of the elements which are attached to carbon atoms, the hydrogen atoms or whatever element is attached to carbon atom, is then fixed at that point, which means if it is present on the right side, then it is supposed to be present on the right side. If it moves on the left side, then it is going to have a different chemical property. So due to this reason, this creates a geometric isomerism, in which there is cis trans isomerism. Of course, this problem can be solved if we can provide high amount of temperature. If this isomeric problem, geometric isomeric problem, can be solved um, if we can exhibit rotational motion in double and triple bond compounds. If let's say if we take butene, and in butene, if we exhibit if we provide it with high amount of heat and high amount of energy to it, then it will cause to break the double bond within it, due to which it would be able to exhibit a rotational motion inside it, due to which there would be no requirement of creating geometric isomers or cis and trans isomers. But since the expense of that energy is quite high, and providing that much amount of energy is not possible naturally within our environment, due to which geometric isomers exist as the solution to this problem. Such that if we talk about, let's say, if we talk about uh, chloro 1 bromo 2 chloropropane, 1 bromo 2 chloropropane. If we talk about 1 bromo 2 chloropropane, it is an organic compound which is having 1 bromide functional group, 1 chloride functional group, or we can also take the example of 2 chloropropane. If we are having 2 chloropropane, let's suppose this is a 2 chloropropane. This is a 2 chloropropane. It is having two functional groups which are known as the chloride functional group or the halide functional group. And 2 chloropropane is there. This is CH3. This is CH3. Right. Now, if the two chloropropane are arranged in such a manner that when we divide them from center, then it causes to create a symmetry of the organic compound on either side, due to which this side is the symmetry of this side, due to which both sides are symmetrical to each other, and both are having equal distribution of carbon, CH3 and chlorine functional group, due to which the this is known as cis cis isomer. But if you talk about trans isomer is opposite of this. Instead, in trans isomer, what we actually have is that uh, the two isomers exist on the opposite position. such that chlorine exists on the other side of the diagonal and CH3 exists on the other side of the diagonal, due to which the CH3 existing on other side of the diagonal, chlorine existing on the other side of the diagonal will cause not to form a geometry, which means if we divide them vertically, if we divide them horizontally, we are unable to see a symmetry in their structure, due to which when there is no symmetry, then it is known as a trans isomer. This is example of trans isomer. So this is known as trans chloropropane, trans 2-chloropropane, and that one was known as cis trans. Sorry, that's why this one is known as trans 2-chloropropane, and that one was known as cis 2-chloropropane. So this is all about the concept of geometrical isomers. Hopefully you enjoyed the video. Hopefully we meet again another.